because these are the most common mistakes I've seen students make. And so it's the same consistently each year. I talked about it, but you don't really understand the misconception until you experience it. So let's look at this. So first things first, does everyone have the equation typed into their calculator? Y'all, what kind of front of the room is that? Y'all like hiding in the back. Y'all sitting down. Come on, get involved in this conversation up here, okay? I'll just pull this down. All right. Or continue sitting on the back counter. Y'all ain't that cool? Get up here. Like, oh, Mr. Kenny, I'm too cool to come up and talk in the class. Y'all still are not like even close to the center. Come on, come for it. I'm not going to bite. I'm not going to hurt you. I need you involved. I need you closer. The closer you are, the more engaged you are. That's just how it works. Look, do we all have our equation in? Thank you, Miles, for moving forward a little bit. Do we all have our equation typed in? All right. So here's what I first need y'all to do is I want y'all to go to Zoom Standard, okay? So it's going to look like this. And I want to emphasize and remind y'all of a couple of things. When I look at this, do I need to zoom super far out or anything? No. Realistically, you see how much dead space is over here? Anyone know what I mean by dead space? There's nothing graphed there, right? Like I don't see anything in that space. Dead space over here. So I'm actually going to shrink my x, but very clearly my y goes past this, my y goes past this, so I need to change the y. But what I want to do first is I want to talk about this. So everybody with a calculator in hand, hit Menu, Analyze Graph, and I want you to click on Maximum. Okay? And so this function, a lot of us are very clearly seeing it, it increases here, right? And so I want you to do a lower bound to the left of that, and I want you to do an upper bound to the right of that. I'm just going to keep going right. So it doesn't have to be super far right, but if I go right here, okay, for my upper bound-ish, and I hit enter. Whoa! That just changed things drastically, right? Is that what I really want to see? Listen, when you do maximum, the calculator can't think for you. When you do maximum, that calculator is going to find the highest y value for that interval that you had. So when I did the gray over to here, then it found the highest y value within that region, which is this number right here. But that's because it's not a maximum. Hear me very clearly on this. Infinity is never a maximum. Can you actually ever get to infinity? No. Infinity is not a maximum. On top of that, leaving my tops off the expo markers. Ugh. Okay, so I don't know if y'all know this. Does anyone know what Control-Z does on a computer? Uh-huh. Never heard of that? Does anyone know what Control-C does on a computer? Or on a Mac it is? Say again. That's copy, right? It's a shortcut for copy. Control-V or Command-V is paste, all those kind of things. Control-Z undoes something. These are just like computers. So if you hit the Control button, then the letter C, it'll undo it. You might have to do Control-Z twice. But notice how it just undid what I did. Okay. So from here, though, let's go back and let's actually change our window settings. Remember, I don't want to zoom in. I don't want to zoom out. If at all possible, I'm going to go to Window Settings. And remember how we said we need our x smaller. So I originally typed in -6 to 6. And I wasn't sure about the y, so don't do this y yet. But I want to just remind you, I did -15 to 15 originally. And looking at this graph, can I see all of my extrema here? Sure about that? Can I see this extremum down here? So if you type in window settings and it doesn't show you everything, then just do it again until you see everything you need to see. Okay, so what I ended up doing under window settings was -25 to 15. I saw my maximum, but there's my y minimum. Now, can I see my zeros? Can I see my maximum? Can I see my minimum? Can I see those key features? Yes. Now, here's a couple of things that I need us to remember and in a second make notes about. when we say relative maximum, that's the highest point for that area. Okay, so relative maximum is the highest point for that area. And remember, I talked about this last time, where a relative maximum is when the function stops what? Increasing and starts to decrease. When I look over here, does it ever start to decrease? So that's not a maximum. A relative maximum, it is where, or it's the value, which don't forget value means the what? Which value am I referring to? The y value, right? The value of f of x, or my output, my y value. So the value of f of x where the function stops what? Stops increasing and starts to what? Decrease. We should hopefully already have this in our notes, but if you don't, we need to make sure this is very, very, very clear. It is where the function stops increasing and starts to decrease. So just looking here, how many relative maximum do I actually have? I have two. I have one here, and tell me when to stop. There? Does it stop increasing, start to decrease?
Yeah.
So that's a relative maximum. So, relative maximum. So what's going to be a relative minimum? It's what? Okay, so value of f of x where the function stops decreasing. So, what I want you to do is, if you have not found those max and min yet, find those now. So use your calculator to find those max and min at this point. I'll give you time to take notes in a second. I'm going to talk about some things. So this group, notice we need to do some more here. Because how many maximum do we actually have? How many minimum do we actually have? So we need to find all of them, right? Next unit, we're actually going to learn how to know how many max and min you could have. Two roots.
No, like two, right?
Well, not always, but are there two of them? They're where?
Like right there,
Okay, and?
and then right there.
Okay. So for this one, we need two. I just want to be clear, not every function has two maximum.
Okay.
Okay. Yeah. And how many minimum do we have?
One,
And?
two.
Okay. So find them. Use the calculator. Yes, ma'am. Sheet. Here's this. Oh yeah, there's that. And here's what we're going to work on. Show me what you're doing then. Which one are you trying to do? Yeah. So remember, lower bound means it has to be to the left, upper bound means it has to be to the right. So to the right. Don't go that far. Don't go that far. You need to be just around it, because remember what it's going to do is it's going to find the maximum within that range. Is that within your range? So just stop there. Hey guys, really quickly, I do want to point this out. Look, how many maximum can the calculator find at a time? One, right? So if I want this one right here, I need to be to the left of it, hit enter, and then I just need to go to the right of it. As long as that maximum is within that gray region, you found it, don't keep scrolling past that, because it can only find one at a time. Same thing with my x-intercepts. How many x-intercepts can it find at a time? One. Okay. What?
Excuse me.
You're excused.
I'll put a point down, that's why I was
Okay.
I got put.
So, yes,
I got put.
go for it.
So you know I have 3 or 5.
Yes.
Doesn't mean I put, I was just trying to. Okay.
Okay, so I want to talk about a couple things. Listen, if you've at least got one minimum and one maximum, then you understand how to do it. We got to move on because we got stuff to do today. Really quickly, I heard a conversation between Landon and Bella earlier. Miles is hinting at this right now. What degree did we all agree this function was? Why was it 5th degree? Because the highest power is 5, right? The highest power is 5, 5th degree. So what does the fundamental theorem of algebra tell us, Kyron? It's 5th degree, so what does that fundamental theorem of algebra tell us? Okay, we got to know. Huh? There we go. Technically it says 5 roots. It's 5 zeros. I'll accept that. But I need us to look. Does that mean there's going to be 5 x-intercepts? Why are there not 5 x-intercepts? There has to be 5 roots, right? Say again. We have a double root, right? 1 root, 2nd root, 3rd and 4th root, 5th root. So don't forget, if I ask for the number of x-intercepts, the number of x-intercepts is not always the same number as the number of roots, because some roots can be double roots or triple roots. What other type of roots would not show up on the graph? Imaginary roots, right? I just know that I have to have 5 roots. That does not guarantee they're all x-intercepts. So keep in mind that whether they're x-intercepts or not, and so keep that in mind when I ask you, if there's a double root, that's going to change the number of x-intercepts. It's going to be a little bit less. So keep that in mind for future assessments. From there was something else I was seeing that I want to talk about. So we already addressed this. So one, I do want to point out, how many x-intercepts should we have written? 4, right? There's only 4 of them. It's just one of those x-intercepts is a double root. Relative maximum, should we ever have an infinity for a relative maximum? No. What I would also remind you of is, looking around the room, I see a lot of the similar responses for how we have written our maximum and our minimum, in the sense that we are writing it like a point like this, which remember I told y'all before, so I'm going to pan over here for a second. I've told you before, writing it as a point is okay, but it's a relative maximum blank. It's a relative minimum blank. What's that blank that I'm leaving out? What's that blank I'm leaving out? The relative maximum blank. Relative minimum blank. Value. Why do I emphasize that it's the value? It is the output. When we say a relative minimum and a relative maximum, I'm focused on the output. So I want to emphasize and look over here, because Miles and I were talking about this earlier, and this is a good idea to note. When we say a relative maximum, what it really is the value, the output, at x equals negative 1.62. The minimum is negative 17.8 at x equals 2.47. That's the most accurate way to say this. Relative maximum of 0 at x equals 1. So keep in mind, will I accept those points as my relative max and min? Yes. Now you still need to give evidence for it. And max and min are very clear, very easy with the evidence. If you go back to the definition, we know there's a maximum because the function has what? Go back to the definition. How do we know when there's relative maximum? When the function has stopped increasing and started decreasing. We know there's a minimum when stops decreasing and starts to increase. Go back to your definitions for your justifications. But keep in mind, right, the most clear evidence is it's the outputs at whatever x value is. But when we say a maximum value, a minimum value, we're talking about the output values. So please keep that in mind. I'm trying to remember if there's anything else that I want to add in. Oh, y-intercepts. Did you actually have to graph this function to know what the y-intercept was? Why not? Why? Where is it? Yeah, remember, this -6. Because what do we know about every y-intercept that's ever existed, Sarah?
The x value is 0.
So what's this going to become?
0.
Right, well, -6, right? So literally, if I substitute a 0 in for x, all those terms become 0, and I'm left with a -6. So don't forget, nice and easy for the y-intercept. Domain and range, a lot of us were saying the same thing. The domain is what? -infinity to positive infinity. And so why is that, Miles? And I'm not picking on you, but you were talking about something last time. I want to make sure this is clear. Why is it -infinity to infinity for my domain? We need to go back to this if we're not sure.
I don't know how to explain it.
Ugh.
Because I would explain it, you don't like it.
Not I don't like it, it's not 100% accurate. Because your explanation is only built off of what representation? The graph.
Oh.
But domain and range are true for the graph, for the table, for the equation, for anything. Why is it -infinity to infinity?
You can plug in any number.
So 1, yeah, algebraically, I can substitute any number in, right? That's every number from -infinity to infinity. And you said substitute it what? There's a two-letter word in there. What'd you say? Didn't you say it? No? Who said it? Plug it in, right? So it's called in. When we talk about domain, it's my inputs, right? It's not that I don't like it. You're 100% right based on the graph. But what if I just have the equation? What if I just have the table? I still want all my inputs, which are my x values, left to right. Range, what's my range? Same thing, because graphically, we can see it. Does it ever quit going down? No. Does it ever quit going up? So what are my outputs, right? Focusing on the idea of outputs. What's my outputs?
Oh,
No.
-infinity to?
Positive.
All right. Some of you need different sets of information for this, okay? So what I want to give you time to do right now is to make whatever notes you need to for your future forgetful self about degree, zeros, domain, range, y-intercepts, x-intercepts, relative minimum, relative maximum. I will say I think the majority of us should make some notes about relative max and min. We've got to remember stop increasing, start to decrease. We have got to remember domain and range, inputs and outputs. And then x-intercepts, whatever notes you need to make about that. Okay, so just, let's say 3 minutes, 4 minutes until 8:40, then we will start the next piece, right, Shadidra? So we're awake, taking notes. Okay? If there is something specific you need to ask about during this time, please ask it. Yep, run like one full side. So remember, domain is the set of all inputs, right? And so when we say inputs, first off, you can substitute anything into that equation, right? Like, so domain is anything. But graphically, we can also see this. Yes, this is going down, but it's also going to the left. Is there a going left? So the lowest, so the minimum x value, not relative min, relative max, the minimum x is -infinity. Here, yes, it's going up, but it's also going to the right. Does it ever quit going to the right? So the maximum x is, so it's infinity to positive infinity. When we're talking about range, remember that's my output. So graphically, does it ever quit going down? So my minimum y is -infinity. Does it ever quit going up? So my maximum y is, so -infinity, positive. Does that make sense? Yeah. There's some right there on my shelf, or the bookshelf. One final note that I just remembered that I want to make clear. Actually, two final notes. One, what key points should you make sure your function always has when sketching a graph? Make sure it has zeros, the correct zeros, right? And then to the best of your ability, do your max and your min as well. One thing I will point out as well, right over here, if I can get your attention, I do want to caution against graphing my function, like being careful with graphing my function, because what issue would I have here? It's not a function, right? Now, here's the thing. What I will say is this. Is it hard to graph these sometimes? If you want to just make a note, say, hey, Mr. Kenny, I struggle with graphing, but I know this isn't quite a function, is that still evidence of understanding? I'll accept that, right? Because I know it's hard to graph these by hand sometimes. Try to do your best. We'll do more practice with it. And I will say also, I'll make a bigger graph so it's easier. But I would rather it be a function and not quite have the right maximum there than it not be a function, okay? So even that's not quite perfect, but work on making sure that your polynomial does look like a function. So like this, I'd be good with. This one, a little bit iffier. Okay, so be careful with sketching your graphs. Just looking at this, the second proficiency scale for this unit, I do want to emphasize and point out that we should know quadratic functions, fundamental theorem of algebra, zeros, factors, rate of change, domain and range. We got to know those vocabulary terms. Need to know how to determine standard form of polynomial by multiplying linear and quadratic factors, identify domain, range, and intercepts of polynomial function. Before we do the demonstrated understanding, I want to do a couple questions that tie into this to make sure we get a little bit more practice. But then also right here, determining the multiplicity of zeros or roots, determining the degree of a polynomial in factored form, and the degree in standard form. I'm going to go ahead and say we're probably pretty good at standard form, from what I'm seeing. How do we identify the degree in standard form? It's the highest power, right? But I want to make sure it's clear before we do a demonstrated understanding how we identify in factored form. So like with number 10 here, highest power was 5. But what's the degree in number 7 again? We talked about this one yesterday, I believe. 4. Why is it degree 4? There's a couple ways you can explain it. So it's not always an x-intercept, but it is a, okay, what's another word that ties into x-intercepts? Zeros or roots, right? So, I mean, we can rewrite this as x plus 1 times x plus 1. How many roots are right here? 1. How many roots right here? And how many roots right here? So there are 4 roots. So remember, you would have to identify how many roots there are in each factor. Each factor introduces new roots, new zeros. That's kind of like the idea behind transforming polynomials. So we have 2 roots in one factor, 1 root in another, and 1 root in another. It's just, that would be a double root. So 4 roots, so what degree would this have to be? Degree 4. So use your factors as well. By the way, I would point this out. Could you convert this to standard form? Is that more work than is necessary? You can do it though. Just keep in mind, it's only the highest degree in standard form. In factored form, you want to look at the roots of each of your factors. Alright. That one's lame. Here we go. I want to do this one. So this is also off of Features of Polynomials Practice. This is the last thing we're going to do before they demonstrate your understanding. So let's go move to our vertical surfaces with our small groups, and let's work on this number 2. So it's on the front side of that sheet you were just working with. Yeah, they're all very similar. Okay. Yeah, let's go ahead and work with each other. Answers on vertical surfaces. We're going to come back together in about 6 minutes. Brownie, you want to work with Landon and Bella since... Wait, who else is here for Jade? Drake. Oh, he'll be back soon. Okay, cool. I got you. So, well, remember, this is a standard form factor, right? When you look at x squared minus x minus 6, what type of function is that? When you look at just the x squared minus x minus 6, what type of function is that? Just this piece. It's quadratic, right? It'd be a quadratic with roots at 3 and negative 2. So notice, in the standard form, no, you wouldn't worry about that minus x. In the standard form, a camera, is that fair? You don't want to do the camera? You don't want to move it around? Oh, Davis wants it. I can see it in his eyes. All right, Davis in control. Okay, so first things first, really quickly, we were very, very successful on identifying what type of function this was. What type of function are we looking at? Cubic. How do we know it's cubic without even graphing this joker out? It has 3 roots, right? Notice, and I had a couple of students asking me, and they're like, well, Mr. Kinney, what about this minus 3x? Well, remember, this is in standard form. What type of function is this quadratic? Sorry, what type of function is this factor? I just said it. Quadratic, which is degree 2, and it has how many zeros? Just this quadratic? 2. This linear has, for a total of 3, right? 3 zeros means that it's going to be cubic. Now, the next question is, what are the zeros and what are the multiplicities for h of x? Do the zeros match the x-intercepts for that function? Now, I want to point this out. When I'm talking about this, there will be sections of the test that are non-calculator. This could easily be on the non-calculator portion, okay? So, we've got to remember when finding zeros that the whole function, the output is... Say it loud. 0. There we go. And so we've got to remember strategies to finding this. Now, first strategy is this. The only way to get a product of 0 is if at least what? One what? One what is 0? Input. Output. Y'all didn't set the input, you didn't let the inputs be 0, you didn't let the out. Say again. So you set the equation equal to 0, but we already did that, right? So what's the only way that we get a product of 0? Say again. One of the what? You're closer, but these are not, so that's the thing, not the roots. This is not an equation. What do we call this? A factor or an expression. Notice that x minus 3, does that x minus 3 alone have an equal sign? No, so you can call it an expression or you can call it a factor. And remember, that's the whole beauty of the zero products property. We're multiplying, so at least one of those factors has to equal what? 0. So x minus 3 is equal to 0, or, and I need y'all to pause, I need y'all to remember, because I saw a few of us try to start using inverses right away. But when can I use inverses with properties of equality? When it's in vertex form, but when I see that variable only one time. I'm not using inverses here, it's standard form. So I got 3 options. What are those 3 options? You can use the area model to help you what? So remember, the area model can help you distribute if you have factors. I don't have the factors, I want the factors. So I can use the area model to help me get the factors, right? And it's important to recognize this because if I'm trying to multiply, so Davis, can you scoot over here? So notice if I want to multiply, so one of the questions was go from this factored form to my standard form. And so I put one factor in one of the sections, right? And I put the other factor in the other section. And that helps me get the standard form on the inside. So notice, where do my factors always go in this area model? On the outside. And where does my standard form go? On the inside. So when I'm looking at this standard form here, that has to go where? Standard form has to go on the inside, and I need to get my factors. Okay? Standard form goes on the inside, and I need to get my factors. And so I'll talk about that in a second. But that's only one strategy, to factor it. What's the other strategies that we can use? Say it louder. Because I heard y'all talking about it. What's the beautiful part about that quadratic formula? I mean, ice is slippery. The better question is, why you use ice like that in my classroom? Miles, what did y'all talk about? The quadratic formula what? It always works, right? You can't always factor. Remember, you can only factor when those roots are rational. The quadratic formula always works. What's the last strategy we could have used, but I definitely would not have used here? I could have converted it to vertex form. If you had paid attention to this, remember h is the opposite of b divided by 2a, but that gives me a positive 3 divided by 2 times 2, which is 4. Yeah, I'm good. I'm not using that, dealing with that fraction, okay? So you can convert to that. But remember, you only have to have 2 total strategies, so factoring or quadratic formula would be great options here. Last couple of things I want to point out, and I want to make sure. When I'm looking at this standard form, remember the 2x squared is set. This is where my quadratic term always goes. The constant term is always set. That's where it goes. But remember how there are 2 terms that add up to my bx, right? So Kelly was asking that question, hey Mr. Kinney, how do you know there's always an x there? Well, remember the whole point is that these 2 terms add up to my bx. So those 2 terms need an x. Miles, you had your hand up.
No, I was going to have 2 base plus 3 comes out, but I see what
The what? Oh yeah, we're not there yet. Remember, we have to get our standard form first before we can get our factors. And we had to find this. So how did I help this group find the negative 6x and the 3x? Where's that coming from?
A times C.
So remember, you got to start with a times c. So 2 times negative 9 is negative 18. Remember, I need factors of that can add up to b. And so there's lots of factors in negative 18, but the only 2 that work that add up to negative 3 are negative 6 and 3. Those are the only 2 factors. So that's going to go here. Does it matter where they go here? If you go either order, it does not matter. So don't sweat that. And you just find your greatest common factor for each row and each column, right? 2x squared and negative 6x, that's a 2x. Right? What do 3x and negative 9 have in common? That positive 3. 2x squared and 3x, what do they have in common? And notice that makes sense. What's 2x times x? What's 3 times x? See how that it makes sense once you have this filled out. And so what do negative 6x and negative 9 have in common? Negative 3. And so there's my factored form. And so I could have written this from the beginning as x minus 3 times x minus 3 times 2x plus 3. Right? But what I'll point out is right here, x is equal to what? What are my roots here? X equals 3. Thank you, it's positive 3. Remember, we need the opposite, right? Yeah, x equals 3, but it's twice, so it's a multiplicity of 2. Here, we get 2x plus 3 is equal to 0. 2x is equal to negative 3. And remember, this is the clear case of why we want that zero product property, because it's not always just the opposite of this. Sometimes we gotta do that. And you'll notice for those of us who did it graphically, Kyron, can you move to the side real quick? Those of us who did it graphically and looked at the x-intercepts, they got 3, 0 and negative 1.50. There's my negative 1.5. Last thing, Davis, can you scoot this way for me? Notice this group used the quadratic formula. Right here, they did b squared minus 4ac. 9 minus 4 times 2 times negative 9 is what? 81. Nice and beautiful, right? Notice how we had rational zeros over there? Well, it's because the square root of 81 is an integer. So, positive 3 plus or minus 9, all divided by 4. And they broke it up here. I love that. What's 3 plus 9? 12 divided by 4 is?
3.
Is that the same 0 we got over there? 100%. What's 3 minus 9?
Negative 6.
Negative 6. And if I take negative 6 and I divide that by 4, it doesn't perfectly divide, but they do have the common factor of 2. So negative 3 halves. Is that the same 0 we got over there? So does it matter which strategy you use? You just got to learn how to think with it. You got to slow down and pay attention to those things. One thing I do want to caution is right here. I just noticed this. Remember, this is b squared, and my b is negative 3. So we want negative 3 squared minus 4 times 2 times c, which is negative 9. I think what y'all did is you based it on this cubic, didn't you? Okay, but remember, this is what formula? Quadratic formula. This formula only works with what type of function? A quadratic function, right? So remember, you could have already found the 0 from x minus 3. You just had to find the zeros from this quadratic. Does that make sense? So be careful with that. And then multiplying the factors using that area model to get the standard form. Oh, because there's x equals 3 with a multiplicity of 2 and x equals negative 3 halves, are we going to see the same number of x-intercepts as zeros?
No.
Why not? We got a double root right here. How many x-intercepts am I actually going to see on this graph? I only saw 2 x-intercepts. One's a multiplicity of 2. It bounced there. It's a double root. What are your questions before we do it? Demonstrate your understanding. All right. I'm going to give you all 25 minutes, so the rest of class, we'll go over this tomorrow to start class. I'm going to give you a calculator portion first. So you may have a calculator on your desk. You will need to clear that calculator off your desk before